inverting a function, what do you do to it? Inverses. You spent all last year looking at different inverses, Olivia. Reflection over the line y equals x, correct. And, all right, so let's start with that. So our guide for inverse sine is going to be sine of x. So I'm just going to, let's see how I want to do this. I'm not going to label the x-axis, and you're going to see why in a minute, but I'm just going to, first of all, I'm going to darken my x and y-axis because they're not very dark. And then I'm just going to go as if this is, well, maybe I will. 1, 2, 3, 4. And let's say I go up to 1, back down to 0, so that would be pi, down to -1, back up to 0, so that would be 2 pi. Make sure you're definitely using a pencil today. And then if I continue that a little bit on the other side, -pi, -2 pi. Okay. Here's the issue. First of all, flipping this over the xy line, x equals y, is going to be something. It's tough to visualize because of the wave. But also, this is currently a function, right? If we take the inverse of this entire, interval from like -infinity to infinity, the inverse will not be a function. Why? What does this one fail that tells us that its inverse will not be a function? Aiden? Horizontal line test. So this is a function because it passes the vertical, but its inverse will not be a function because it fails the horizontal, right? In other words, when we flip this over, the line y equals x, it's going to fail the vertical line test, but we don't want that. We want the inverse function to still be a function, okay? So knowing that, we only are going to be looking at a section of this graph that passes the horizontal line test, okay? So, and that section is from here to here. This is the section along which we're looking at the inverse function simply because that little section passes the horizontal line test. And it's the most central section that does that. So I'm actually going to get rid of all of this. And we're only going to be inverting this section of the sine graph. So I'm going to start with a table of values for just that. So this is -pi/2, right? -pi/2, and the y coordinate is -1. And then we'll do a few more. So if you think about your unit circle, we're only looking at from -pi/2 to +pi/2. We're only looking at quadrants 1 and 4. So what's the next critical angle in -pi/, well, if we're kind of going from small to big, what's the next critical angle? What's the reference of the next critical angle? Pi over oh boy. You've got, every quadrant has 3 critical angles. What's the reference angle of this one, Mitch? Pi over 3. So how many pi's over 3 would that be? Yes, if you're going this way, but we're trying to stay between negative pi over 2 and positive pi over 2. So just negative pi over 3. And then you have negative pi over 4, negative pi over 6, 0, and then positive, go through the ranks, pi over 6, pi over 4, pi over 3, and a positive pi over 2. So since sine is negative in the fourth quadrant, these are all negative values. Sine of 0 is 0. Negative 1/2, negative root 2 over 2, negative root 3 over 2. And in your first quadrant, we have a half, root 2 over 2, root 3 over 2, and 1. So those are the points on the sine function. What do you do with those to come up with the points on the inverse sine function? What's the rule? How do you get the points on an inverse function? Morgan? Yep. Well, that's if you're writing the inverse function, but if you're just trying to look at the new points, you just flip the points. So negative pi over 2, negative 1 will become negative 1, negative pi over 2, negative root 3 over 2, negative pi over 3. So go ahead and do that the whole way down. So this is where this is now going to get a little tricky. Because our original sine graph has an x-axis that is labeled via radians and a y-axis that's labeled via regular numbers. And when you flip it, now your x-axis has to be labeled regular numbers and your y, oops, I put pi over 2 here. And then 1 pi over 2. And your y-axis has to be labeled via pi's. So I'm actually just going to erase this so that I can focus on graphing the inverse sine function. So now we're back to nothing. And before we do it, let's talk domain and range. On a sine curve, any sine curve, your domain is technically unlimited, right? X can be any real number. You can take the sine of anything, but your range has to be between negative 1 and 1. When you go to the inverse, those things are flip-flopped, right? So your domain, and if you look at your numbers, obviously is only between negative 1 and 1. And your range, it would be all real numbers, but remember on this one, we had to look at a restricted section of it, right? And the restricted section was negative pi over 2 to positive pi over 2. And so that's going to be the restricted range of our inverse sine function. In other words, when you are asked to find the inverse sine of anything, as long as it's between negative 1 or 1, you'll always get an angle that's between negative pi over 2 and positive pi over 2. You can do it on your calculator, no matter what. Now I should probably do degrees, just so this makes more sense to you. If I do inverse sine of, I have to plug in something between negative 1 to 1, Because if I don't, like if I do inverse sine of 2, it's going to be an error because it's not in the domain. But inverse sine of 0.9 will give me an angle between, and I'm in degrees right now, negative 90 and positive 90. Agreed? If I do inverse sine of, again, I have to pick something between negative 1 and 1, so if I do 0.5, oh, that's an easy one, I'll do 0.1. I get something that's between negative 90 degrees and positive 90 degrees. If I do inverse sine of negative 0.7, I get something that's between negative 90 degrees and positive 90 degrees. Follow? Okay? So, what does this look like? I'm going to scale my x-axis from negative 1 to 1. I'm going to spread it out pretty heavily, though. 1, 2, 3, 4, 5, 6 units I'll call negative 1. And 6 units out I'll call 1. And then my y-axis has to be from negative pi over 2 to pi over 2. So I'll let that be positive pi over 2. And that, I went out 8 units. That way 4 units out is pi over 4. And then I can sort of figure out everything else accordingly. So, just out of curiosity, what does each hash mark count for? If every 4 units is 1 pi over 4, if you divide pi over 4 into 4 parts, what does each one of them stand for? Pi over 16, 1 pi over 16, 2 pi over 16, 3 pi over 16, 4 pi over 16, if we need that. Just worth knowing, okay? So, negative 1 maps to negative pi over 2. Negative root 3 over 2, we need kind of a decimal 4. 0.866, so negative 0.866. So negative, uh-oh. I cut this up into 6. That wasn't very nice of me. Maybe I should have done it into 8s. Hold. I'm going to move this out 2 more units. So negative 0.75 would be there. So negative 0.866 would be right about there. And that goes to negative pi over 3, which is, how many pi's over 16-ish? Just under 5, right? Because that would be, to get to 16, I would multiply by 5 and change. So I'd multiply that by 5 and change, so negative 5 and a little bit more. You follow that? Negative 0.866, and then 1, 2, 3, 4, 5, and a little bit more. And then negative root 2 over 2 is negative 0.7. There's 0.75, so negative 0.7 is right around there. And negative pi over 4. And then negative a half. And negative pi over 6, which is times a little more than 2.5. So like a little more than negative 2.5. Negative 1, 2.5. 16, we're going to go there-ish. And then 0, 0. You are not going to have to get that specific about the points in between. Obviously, it's hurting our brains. But there's the first section of it. And then when you go to 1/2 pi over 6, here's a half. Pi over 6 we said was like a little over 2.5 pi 16ths. So there. Root 2 over 2 was 0.7. There's 0.75, so 0.7 is right there. Bring it to pi over 4. There. Root 3 over 2 is that 0.866 number, so 0.75, so 0.866 will probably be right around there. Pi over 3 is a little bit more than 5, we said. 1, 2, 3, 4, 5, and a little bit more. And then 1 in pi over 2. So it does that. And there are not arrows on the end of this. So we essentially took just this section of the sine parent graph, and that's the sine one. Are you back up here? So they're kind of on the same. And then this one goes up like that. I didn't mean that. It should come back across like that. Yes? You see the curvature of it? So it's hard to do them on the same graph with scales because of the reason of their axes being very different. But there is one, I believe there is an image in the book that kind of scales the x-axis with regular ones and with the pi stuff, and does the same with the y, and you kind of see that all happening. So your blue, it's hard to tell because they are very close to each other right there, but if you do look at the blue, it's got that curvature, and then look at the red, which is the sine section. You can see now the reflection over the line y equals x. Okie doke? Okay. The cosine curve, flip to the back. We'll go back to those values in a minute. The cosine curve parent graph looks like this, right? Fails the horizontal line test. So the section of it that we will be looking at is just from here to here. So the domain of the cosine parent graph, the domain that we'll be looking at is from 0 to pi, and the range, as always, is -1 to 1. Which means when we flip it and we look at the inverse cosine, our domain is -1 to 1, and our range is 0 to pi. So what that tells us is that any time we take the inverse cosine of something, we have to get an answer between 0 and pi. That's different than with the sine that we saw on the other side. With the sine graph, we had to get something between -pi over 2 and pi over 2. And I showed you a gazillion examples on the calculator where that happened. The sine, inverse sine, stays in quadrants 1 and 4. That's -pi over 2 to +pi over 2. Inverse cosine stays between 0 and pi, so that's between quadrants 1 and 2. So anytime I use the inverse cosine function on the calculator, I will have to get an answer that's between 0 and pi in quadrants 1 or 2, between 0 degrees and 180 degrees. Do we follow? Okay. So to graph the inverse cosine, I'm thinking of the cosine table of values on a domain of 0 to pi. I'm just going to do the easy ones, like 0, pi over, I'm taking the cosine, so pi over 3 is nice, pi over 2, 2 pi over 3, and pi. I didn't do pi over 6. I didn't do pi over 4 because those decimals are ugly, right? The cosine of 0 is 1. The cosine of 60 is a half. The cosine of pi over 2 is 0. The cosine of 2 pi over 3 is negative a half, right? Once we get into the second quadrant, cosine is negative. And then the cosine of pi is negative 1. So when I'm doing my inverse cosine graph, I'm just flipping all of those. So rather than 0, 1, 1, 0, a half pi over 3, 0 pi over 2, negative a half 2 pi over 3, and negative 1 pi. So on my x-axis, I need to go again from negative 1 to 1. I'll go out 8 again. Why not? Keep it consistent. And then I've got pi's over 3's and pi's over 2's, so I'm going to count by 1 pi over 6. Pi over 6, 2 pi over 6, 3 pi over 6, aka pi over 2, 4 pi over 6, 5 pi over 6, 6 pi over 6. Are we good with that? Does everyone see how I did that? And I'm doing less points so that we don't have to find a denominator to work with 2, 3, and 4, and 6, although 12 would have been the one. I just didn't have 12 units. Okay, so 1, 0, a half, and 2 pi over 6. 0 and pi over 2. Negative a half. And 2 pi over 3, which is 4 pi over 6. And then negative 1 and pi. The book doesn't actually put these two on top of each other, although it does show you the inverse cosine. Based on the way they scaled, theirs is a little bit more vertical looking, right? Do everyone see that? Because I scaled differently, but you still have like the decreasing and then continues to decrease, but the inflection changes. Okie doke. And inverse tangent, your tangent graph has asymptotes at negative pi over 2 and positive pi over 2. And that section in between does already pass the horizontal line test. So I will, this domain that we'll look at will be from negative pi over 2 to pi over 2, except for with parentheses this time. And your range is negative infinity to infinity. When you invert it, your inverse tangent will have a domain negative infinity to infinity, but a range of only negative pi over 2 to pi over 2. So again, think about that. For inverse tangents, any value you take an inverse tangent of has to give you something between negative pi over 2 and positive pi over 2. So it's back to quadrants 1 and 4, like the sine curves were. And that is arguably the most important thing that you're going to take away from this. is why when I take the inverse tangent and the inverse sine, do I have to have an angle between negative pi over 2 and positive pi over 2, versus if I take the inverse cosine of something, I have to have an angle between 0 and pi. And it has to do with how you have to cut the original function in order for its inverse to be a function and pass the horizontal and vertical line test. Okay? So without sketching it again, there's your tangent function that we're looking at. There's your inverse tangent function with all those points flip-flop. See how your range is between negative pi over 2 and positive pi over 2? And your domain, this one does have arrows on both ends. Negative infinity to positive infinity. Follow? Okay, so it'll look something like that. If you just want to sketch that, you can just put an asymptote at negative pi over 2 and positive pi over 2. I don't even know if that's spaced out right, but just so you get the basic image of it. Okay, so the graphs are one thing. Being able to actually evaluate inverse sines, cosines, and tangents without a calculator is another. Okay? So when you're asked for the exact value of inverse sine of root 2 over 2, you're essentially being asked the sine of what angle equals root 2 over 2. So this is going to go back to your memorized values. But as you know, there are a lot of angles that have a sine of root 2 over 2. Based on the range of inverse sine having to be an answer between negative pi over 2 and positive pi over 2, with brackets, you have to give the only angle, and there's only one of them, between negative pi over 2 and positive pi over 2. In other words, what is the angle in either the fourth or the first quadrant that has a sine of positive root 2 over 2? Pi over 4. Since the sine is positive root 2 over 2, it's definitely first quadrant, and then pi over 4. So this equals pi over 4. Inverse sine of root 2 over 2. Now mind you, my calculator's in degrees, so I should get how many degrees? 45. Nope, I didn't mean to hit inverse sine of pi over 4. I meant to hit inverse sine of root 2 over 2. And I'm supposed to get 45. Yes? Okay? Because in reality, there's a lot of angles. All students take calculus. Pi over 4 has a sine of root 2 over 2. 3 pi over 4 has a sine of root 2 over 2. 9 pi over 4, and so on and so forth. Okay? You just have to know to take the one between quadrants 1 and 2. So inverse sine of negative 1/2. So sine of what angle equals negative 1/2? So we have to pick something in the first or the fourth. Because the sine is negative, it has to be in the fourth. This is negative pi over 2 and this is positive pi over 2. What angle is this that has a sine of negative 1/2? Sine of what equals a half? 30 degrees, or a reference angle of pi over 6, but we're in the negative quadrant, so that angle is negative pi over 6. Okay? When you do cosines, cosine of what angle equals negative root 3 over 2, you have to give an angle in the first or second quadrant, and that's up to you to memorize. Cosine is first and second, sine and tangent are first and fourth. So what is the angle between 0 and pi? First of all, which quadrant should it be in, since cosine is negative? The second, right? What's the reference angle? Cosine of what equals root 3 over 2? Got to know your memorized values, Aiden. Nope. Pi over 6. You just gave me the sine. Pi over 6, so this would be 5 pi over 6 if you want the second quadrant version of that. And the last one, inverse tangent of root 3. So the tangent of what angle equals root 3? And because it's inverse tangent, we're dealing with anything from negative pi over 2 to pi over 2. So it's definitely in the first quadrant because tangent is positive. And what's the reference angle? Pi over, Andrew? 3. And so since we're in the first quadrant, that is what it is, pi over 3. So this equals pi over 3. Okay? So understanding why the graphs look the way they look is obviously necessary, but the biggest takeaway, the place where you will use this the most, is trying to come up with these inverse tangent values on your own.